Hi there, folks. Today we're looking at areas of trapezoids, rhombuses, and kites. And these are other quadrilaterals that we haven't found the area of yet. Keep in mind, though, we've already done parallelograms. And remember, parallelograms, there's a wide array of parallelograms. Rhombuses are also parallelograms. So when you think about a rhombus, yes, we can still do just base times height like we would with any other parallelogram. But rhombuses will have some special ways that we can get the area as well. It has more than one option for getting the area, okay? And those options look more similar to what we see with things like kites. And then trapezoids are kind of their own thing. They look a little bit like a triangle mixed with a parallelogram. And so we just kind of have this hodgepodge of other things we have to remember in terms of finding the area of the rest of these quadrilaterals, okay? So the first one here, the area of a trapezoid, there are different ways that you will see this formula written. I believe the book that we have has it written this way as area equals 1/2 the height times base 1 plus base 2, so the base is added together. Most of the places I've seen it, I prefer this version of the formula, which is 1/2 base 1 plus base 2, 1/2 the base is added, and then times the height. And there's no difference here. It means the same thing. It's mathematically the same thing, but it's easier for me to remember that second one because when you think about 1/2 the base is added together, that's something we've done before. That's the mid-segment of a trapezoid. Remember, the mid-segment is that line that's halfway up here. And remember, that guy is the average of the two bases. And that's kind of what we're seeing here. So the average of the two bases times the height. You could really say the formula here is the mid-segment times the height. Would be another formula version that you could have. And that's kind of how I remember this formula. I just think of mid-segment times the height. So the average of the bases times the height. So 1/2 base 1 plus base 2 times the height. All right. You can use whichever version of this thing suits you the best. Some students like the first one better because you're doing 1/2 times a single number and then times the addition, okay? I like to think of it as the mid-segment, but either way, any one of these is fine, all right? So if I look at this guy, for example, we have this trapezoid. I have to do 1/2 the height times the bases added, or 1/2 the bases added times the height. Either way, I just plug it into my formula here. When I look at this one, these are my two bases. Remember, the bases of the trapezoid are the two parallel sides. And then this guy's my height. And once again, the height is measured at a perpendicular angle. It has to be measured that way, or it's not really a height, okay? And so once again, this is the way I approach it. I'm going to do the second version of the formula first here, and then we can kind of switch it up as we go. But that version, it says 1/2 the bases added times the height. And if I were to actually plug this in like I'm doing the formula, just kind of plug and chug, just slapping these things in here, that's a 4.6 plus a 3.5 times the height, which is 2. And now I just simplify. Inside the parentheses, that gives me an 8.1. And then as I continue to multiply, that's a 4.05 times the 2, which gives me an 8.1. So I'm back to that 8.1, okay? And that's square centimeters, all right? Now, when I actually do this formula, I jump in right around this step right here, okay? And the reason I can jump in right to that step right there is if I understand that 1/2 the bases added together is the mid-segment. Well, the mid-segment we kind of thought of as just the average of the bases. So I just say, hey, what's the average of the bases? So I add them together, divide by 2 on my calculator or in my head, and I get 4.05. And so really what this translates into is, the mid-segment times the height. And I multiply those and it gives me the area, okay? That's why I like the second version of the formula just a little bit better. Some students prefer the first version of the formula, and here's why. And really, it's the same thing. We're just doing it in a slightly different order. The reason they prefer this, and if you're plugging the values in from scratch, this one might save you just a little bit in terms of the steps. And here's why. Because right now, when they go to do this, they'll do these 2 steps at once. And I could have done these 2 steps at once in the previous one, but we just don't think of it. I could do the 1/2 times the 2 and get a 1, and then do what's in the parentheses and get an 8.1, and now multiply the 2 and get an 8.1, okay? And so really it cuts out one step if we do the multiplication and the addition at the same time. Okay, so figure out which formula works for you, which makes the most sense for you, and then just plug it in, folks. Okay. If I look at this one, it says Nevada has the approximate shape of a that looks like the figure below, so it's approximately a trapezoid. And so when we look at this trapezoid, I want to find the square mileage, so I just have to find the area of this trapezoid. And so when you look at this, once again, you have to determine which of these are the bases. Remember, the bases of a trapezoid are the parallel sides. And based on the fact that these are both 90-degree angles, that makes this the transversal, and these are the parallel sides. That's the important piece of this thing, is you just have to identify which pieces are which. And so if the parallel sides are the 205 and the 511, well, then those are my bases for this thing. Okay, and so let me do the two versions of the formula. Again, I'm going to use kind of my shortcut version here and say, okay, 1/2 the bases added together is really just the average of the bases. It's like finding the mid-segment. So on my calculator, I do the 205 plus the 511, and I divide it by 2. And so I say the mid-segment, or the average of the bases, is 358. And now I just have to multiply that by the height. And the height on this one, if you rotate this thing and think about the height as the perpendicular measurement, well, that's the 309, okay? And so on my calculator, I just have to multiply these two things. And it looks like it gives me an area of 110,622. And again, that's square miles, okay? If I'm plugging into the actual formula here, here's what it looks like. Let me do the 1/2 times the height, which is 309 this time. That's a terrible looking 3. And then times the bases added together. And so as I simplify this thing, I might take the 309 times the 1/2 first, and gives me a 154.5. Inside the parentheses here, I can do the 205 plus the 511 as well, which gives me 716. And then on my calculator, I can multiply those two things. And just like before, it gives me the 110,622 square miles. Okay? So again, just figure out which version of the formula you're going to use and plug it in. All right? I like one version, you might like a different version. All right? If I look at this one, it says find the value of the area. And so for this one's a little bit tricky, because notice the height is not given this time. And so I have the bases, and I can tell that those are the bases. Those are the parallel sides based on these angles over here. And so I have the bases of this thing, but what I'm missing is the height. All right, so let me draw a height. So one of the sides of this thing, this would be considered a height over here. But let me draw the height over on the other side. Let me draw it right here. And so again, when I measure the height, I have to measure at a 90-degree angle, which means this is a right angle, which means this is a 30, 60, 90 triangle. And so if I think about this for a moment, if I were to kind of cut this side right here, this side would be 5 meters, and over here would be 2 meters. And I know that because of segment addition, the whole thing is 7. And based on the fact that I've created a square inside of this trapezoid, I know that the opposite sides would each be 5, so I can find these different pieces. Well, I have the shortest leg of the 30, 60, 90 triangle. Right away, this side is twice that. That's the 4 meters. This side is that guy times root 3. And so we're using our special right triangle to come up with some of these missing pieces. And so as I look at this thing, the height is the 2 root 3, and the bases are the 5 and the 7. So now I can jump on over to my formula. Once again, if I was doing this, I would just say, hey, 5 plus 7 is a 12, divided by 2 is a 6. That's the average. So I would do the area this way. I would do the average of the mid-segment, essentially, times the height. Okay? Or we come over here and we plug it into our full formula. So here we go. And for this one, it's 5 plus the 7. And as you start to simplify this thing, leave it in radical form until the end. And so here I do the 1/2 times the 2, cancels out, so it's just the square root of 3, and then times the 12. So on my calculator, the square root of 3 times the 12. And so as a radical, if I wanted the exact value, the area would be this. But if I wanted the rounded off answer, the area would be a 20.78 square meters. So that was a terrible looking approximation symbol. Much better. Okay? And depending on the question might ask for the exact value, or it might ask for the rounded off answer. So you just have to kind of play it by ear on that. Okay? All right, so the area of a rhombus or a kite, we can kind of use this special thing using the diagonals to find this. And again, for a rhombus, because a rhombus is a parallelogram, you can still just do base times the height if you have those things, all right? But sometimes we don't have the base and the height. If we only have diagonal measurements, well, then I can still find the area of a rhombus. I can't use that for other parallelograms, but it works for the rhombus, and it also works for the kite. And because it works for the rhombus, it also works for a square as well, because that's a rhombus and a parallelogram. So we have these different methods. So just in case we don't have the right information, I can still find the area of this thing, all right? And so for this one, its area equals 1/2 diagonal 1 times diagonal 2. Remember, there are always two diagonals inside of a quadrilateral connecting the opposite corners, connecting the opposite angles. And so if I just do 1/2 those diagonals multiplied, it'll actually give me the area of this thing. All right. And this comes from, you can kind of prove where this comes from as you look at the individual triangles that are formed in here and finding the area of each of those triangles, then multiplying by 4 because there's 4 of those triangles, that kind of thing. That's kind of where this formula would come from. But it's really nice because it gives us a different way to find the area that's completely using completely different sets of measurements, okay? And so when I look at this thing, if I look at a rhombus, remember a rhombus, I have those two diagonals. Well, I just multiply them and then times 1/2. And then for a kite, I also have two diagonals, and I just multiply them and times 1/2, all right? And that can give me the area of these things. Again, for the rhombus, we still also have the method of base times height. But for the kite, I don't have that method anymore, okay? Because it's not a parallelogram, the only option I have here is 1/2 diagonals times diagonals. And again, as you look at each of these, notice it's just 4 triangles. When you look at the rhombus, it's 4 congruent triangles, and that's where this comes from, and that's why it looks similar. That's why it has the 1/2 kind of thing in there, all right? With a triangle, it's 1/2 the base times the height. And when you kind of think about that, you know, it's interesting because this is like half of diagonal 2, and this is like half of diagonal 1. And if you think about the area of just this triangle, it's 1/2 the base times the height, which is half of diagonal 2. And so when you think about the area of this triangle, what you get is 1/8 diagonal 1 times diagonal 2. But I have 4 of those triangles, so times 4 gives me 1/2 diagonal 1 times diagonal 2. Down here looking at the kite, it's the same kind of thing. It's derived from the same place, except this time we don't have 4 congruent triangles. We actually have to look at the, like this is the only one that gets split evenly. So this is half of diagonal 1, and down here this is also half of diagonal 1. So we kind of look at these triangles as a whole. Okay, and so when you look at that big triangle up top, it's 1/2 the base, which is diagonal 2, times the height, which is half of diagonal 1. Okay, and when you look at that bottom triangle, it's the same thing. And so when you multiply this out, that's 1/4 diagonal 1 times diagonal 2. Well, I have 2 of those triangles, so when you multiply that out, there it is again. Okay, so again, this is based off of the triangles that are created here, but it's 1/2 diagonal 1 times diagonal 2. For example, if I look at this guy, it says find the area. And so if I want the area of this thing, I just have to do 1/2 diagonal 1 times diagonal 2. And it's the entire diagonal when I do this. So area equals 1/2. And so when I look at the entire length of the diagonal, I have to use a little bit of segment addition here. And so for this one, the longer diagonal is a 7. And the shorter diagonal, when I add it all up, is a 6. And so once again, I just plug away on this thing, and that gives me a 21. And that's square inches. Okay? And I'm fairly confident we can plug that into our calculator, do that one in our heads. Okay? This one, it says find the exact area, then approximate the area. And so when you look at this thing, right away, I do not have the information I need. When I look at this thing, I look at this rhombus and I say, well, I have the bases, right? So it's just base times height, but I don't have the height. And so you might try doing something like finding the height. So you drop something like this, and maybe you look around and you say, well, I'm not sure what that is. I can't find that because I don't know where this thing gets split. All right, so there's two ways you can do this. You can look at it like this, or you can look at it in terms of the diagonals. Okay, and so if I look at it this way, let's consider the rest of these angles. This would have to be a 60-degree angle, because remember, these have to be supplementary. And so now if I drop this guy, that is a 30, 60, 90 triangle now, which means this little piece right here has to be a 3, and the height has to be a 3 root 3. And so I could do, hey, area of a rhombus, I could use the base times the height technique and just say the area equals the base, the entire base, which is 6, times the entire height, which is 3 root 3. And so the area, the exact area, is 18 root 3. Okay? The other route we can go is we can kind of try to look at the diagonals of this thing. And so as I try to look at the diagonals of this guy, I would have to draw these diagonals. And so if I draw that diagonal and this diagonal, the thing that's interesting to remember about about rhombuses is that these guys come together at a 90-degree angle. They also bisect the opposite sides. So it also gives me a 30, 60, 90 triangle for each of these. And so as I start to hop around this thing, I can say that, hey, if this is 6, that means this piece is 3. And it means that this longer side is 3 root 3. Okay? And when you look at these, because the diagonals bisect each other, that's a 3, and this is also a 3 root 3. And so each of them kind of hinges on this 30, 60, 90 triangle, but now I can use the other formula. Watch this. Area equals 1/2. The first diagonal, the shorter diagonal, has a total of 6. Okay? The second diagonal is 3 root 3 plus 3 root 3, so that's a total of 6 root 3. And now as I simplify this thing, once again, it gives me 18 root 3. And that's in meters squared, so square meters. So that's the exact value of this thing. It also asks me to estimate this thing, so plug it into your calculator, and you get an area of 31.18. And so again, in this particular example, I was able to do just the parallelogram version of base times height, but I could also do the special diagonal version that applies to rhombuses. All right. And so you kind of have to take whatever the situation gives you. This one I could do both, but sometimes I'll only have enough information to use the diagonal version of this thing. Or sometimes I'll only have enough information to use the base times height version of this thing. All right. And that's why it's nice to have this second version. And you have to know it anyway, because it's the only way to find the area of a kite. All right. So again, trapezoids, it's 1/2 the base 1 plus base 2 times the height, or 1/2 the height times base 1 plus base 2. It's like the mid segment times the height. And then for a kite, you do 1/2 the diagonals multiplied. The same thing applies to a rhombus, but remember, rhombuses are special because they're also parallelograms. So you have two versions for the rhombus, base times height or 1/2 the diagonals multiplied.